This next thing just demonstrates how he knows the context of the conversation we're already having, and he makes a reply based upon the context we're already having. I just say, also, Wolfram has investigated this possibility. That's all I said, okay? But he knows what we're talking about now, okay? So he comes back, and he comes right back. Watch this, man. Yes, Stephen Wolfram is a well-known researcher who has explored the possibility that the universe might be fundamentally computational or information-based in nature. In his book, A New Kind of Science, Wolfram argues that the simple computational rules can give rise to complex and rich patterns and behaviors that resemble those seen in physics systems, and he suggests that the universe might be ultimately based on a kind of cosmic computation or information processing. Wolfram's work has been influential in the field of computational physics and cellular automata. See? There you go again, cellular automata. And it has inspired many researchers to explore the idea the universe might be fundamentally computational or informational in nature. However, it is important to note that this idea is still speculative. There's that word again, okay? And that there is no currently nor direct empirical evidence to support it. I don't know. I think we can have positive proof at this juncture, but okay. Moreover, some scientists and philosophers have criticized Wolfram's approach to being overly reductionist and for neglecting the complexities and richness of the physical world. While computational models may be powerful tools for understanding certain aspects of the universe, they may not capture the full richness and complexity of the physical world as we experience it. And he implies consciousness as well there when he says richness, okay? Can you believe this guy? I mean, it's just too much. It's like talking to the smartest person you've ever talked to, and he knows exactly what you're talking about as well, okay? Now, here we go. You know who Brian Woolworth is, you know. Go look up his book. Look at his acknowledgments. He's got my name in his acknowledgments in his book. Right there, it says Marty Wollner. Okay, anyway, I say also, Brian Woolworth has investigated quantum realism. And apparently he knows about this book too, right? Or maybe either that or he researched it between the 1 second between this input and the reply. I don't know. Maybe he's that smart because it is an online book, okay? He goes, yes. Brian Woolworth is a researcher who has proposed a theory called quantum realism, which suggests that the universe might be fundamentally information-based with a physical reality arising from the interactions of information at the quantum level. According to this theory, by the way, this book, it was like the first one of the first ones that sort of led the way of this kind of thinking. According to this theory, there's another one called It from Bit. There's a bunch of older ones, actually. The universe is like a giant quantum computer that processes information and generates physical reality as a kind of emergent property. Emergent property, that's what I'm saying, okay? Woolworth argues that this perspective can help explain the strange and counterintuitive phenomena of quantum mechanics, such as entanglement and superposition, which are difficult to reconcile with classical physics. Yeah, man, it's really entanglement, man. All you gotta do for entanglement, you just have to use the same particle list index in two different locations, okay? And superposition, all you have to use is two different particle indexes in the same location. There's entanglement and superposition described very simply according to my simple terms of what I call my simple digital physics explanations, right? Entanglement is where you have the same particle in two different locations at the same time, okay? Superposition is where you have two different particles in the same position at the same time. I call that co-occupation. Wollner's theory is still controversial and speculative, and it has not yet been widely accepted by the scientific community. Some critics have argued that the theory does not provide a clear explanation for why physical reality should emerge from quantum information, or how the information in the universe is structured and organized. Well, as far as the emergence part of it, I mean, I'm coming out with this auto-instantiation idea, okay? And as far as the structure, well, I got some data structures defined, okay? So, I mean, it's pretty easy, I think, you know? However, I've looked at Brian's work. He's got a lot of thought to it, just trust me, okay? However, quantum realism is an interesting and thought-provoking idea that has generated much debate among physicists and philosophers, and it remains an active area of research in the field of quantum mechanics and information theory. One thing Brian came up with all on his own, you know how like the outer shells, when it gets to the p orbital, there's two levels of it, and it goes to iron, and there's all of a sudden more levels at that juncture. I think Brian has an explanation for it. It's got to do with loops of like these loops that explain the structure of how the elements are organized. Anyway, yeah. I mean, he's got that answered, and a lot of people don't have that answered. Okay, I'm not doing him any justice the way I just explained it, but he does have that answered. Now, here you go. I was wondering if he looked at my stuff too. You know, he looked at Brian's stuff. He's looked at Stephen Wolfram's stuff. Maybe he looked at my stuff too. I say, Marty Wollner has investigated, quote, explain the reverse time ordering of light. That's the name of my books, you know. And the old bucket. I'm not familiar with Marty Wollner or his work on explaining the reverse time ordering of light. However, as all I said, reverse time ordering of light, he jumps right on. He goes, I can provide some general information on the concept of time reversal in physics. And he gives great explanation. He goes, in classical physics, the laws of physics are symmetric under time reversal, which means that the behavior of a physical system should be the same if time were reversed. However, in quantum mechanics, this symmetry is broken in certain cases, such as when observing the behavior of subatomic particles. This can lead to some strange and counterintuitive effects, such as the apparent reverse time ordering of light or other particles. One possible explanation for these phenomena is the idea of retrocausality, which suggests that future events might influence the behavior of particles in the past. However, this idea is still highly controversial and speculative, and there's currently no direct evidence to support it. Now, I don't want to get off on too much tangent, but Feynman has the idea that the light can find the optimal pathway by somehow pulsating backward and forward through time, and I'm not sure if it collects samples or not. I actually discussed that in him a little far below here, but it's really interesting that he's all over this stuff. He's suggesting that give me a second here. Well, anyway, Feynman is suggesting that light can hit its target by somehow fluctuating back and forth, and therefore, if you move a target, well, in the future it could cause changes in the past and stuff like that. Okay, so that's suggesting that there's fluctuations of time back and forth. Okay, he's saying no direct evidence to support it, but I mean, I'm not sure if this is actually within the definitions of the Feynman path integral or not, what they're suggesting here. The idea of retrocausality, I'm not sure that's directly involved with Feynman path integral. I think it actually is. But they're saying there's no direct evidence to support it. But I think there actually is evidence to support the Feynman path integral as being able to predict the statistical outcomes of going forward in time, where light would go forward if you run through his calculations like that. Okay. It's also worth noting that the concept of time reversal is closely related to the concept of entropy, which is a measure of disorder and randomness of a system. In many cases, the arrow of time, here we go, arrow of time, baby, or the direction of causality is determined by increase of entropy over the time. This means that the future is typically more disorderly than the past, and that events tend to unfold in a certain direction. However, there are still many open questions and debates in physics regarding the nature of time and causality, and our understanding of these concepts is constantly evolving. Well, that's cool. He's just giving me a heads up on the idea of when I mentioned a term. I said reverse primordial light. He's coming back. He's explaining some retrocausality and symmetry and stuff like that. A lot of this has to do with what I'm talking about as well, but some of it doesn't. Okay, I'm specifically zeroing in on the Feynman path integral. Okay, excuse my stuttering. Okay, here we go. I say Feynman has investigated the optimization of pathway selection of light. Now, I should have said at this juncture, the rule of least action, okay? Which, I've already talked about in the previous videos, okay? He says, I'm not aware of a Feynman investigating the optimization of pathway selection of light specifically, but Feynman did make significant contributions to our understanding of the behavior of light and the quantum nature of electromagnetic interactions. He goes on and on to talk about Feynman's work with QED and stuff like that. I'm going to read it to you real quick here. It's just amazing that I'm talking to a computer here. But this is what I was actually talking about. And actually, he winds up apologizing for this. Watch. Just watch this. It's amazing. Is this... I don't know. You guys are bored? Just go ahead and hang it up. But, man, this is really thrilling to me. Feynman developed a mathematical framework known as Feynman diagrams, which provide a way to visualize the quantum interactions between particles. These diagrams can be used to calculate the probabilities of various particle interactions, including those involving light. Feynman also contributed to the development of quantum electrodynamics, that's QED, which is a theory that describes the interactions between light and matter. QED is based on the idea of virtual particles, which are particles that can briefly pop into existence, interact with other particles, and then disappear again. And he shows this in his Feynman diagrams, okay? This theory has been extremely successful in explaining many phenomena, including the behavior of light in various contexts. So they're able to analytically apply these theories to real measurements, and it comes out, works pretty good, okay? Regarding the optimization of pathway selection of light, there are various ways in which light can be directed and controlled, such as use of lenses, mirrors, or other optical components. In recent years, there has been significant progress in the development of new materials and structures that can manipulate light in novel ways, such as metamaterials and photonic crystals. These advances have opened up new possibilities for the optimization of light pathway for a range of applications, including communication, sensing, and imaging. And don't forget, they got this new stuff. They're called Bose-Einstein concentrates. They're like these really super cold and condensed particles, like globs of them. They're super cold. They're almost absolute zero, right? And when you shine light through those, it slows down to, you can actually see it moving, man. It's got like a refractive index like in the millions and billions. You know, it slows light down. You can actually watch it moving, and that's going to really advance the new studies on light, how it works. Yeah, that's what I'm thinking anyway. Okay. Now here's where I straighten his ass out here. I bitch slaps the computer a little bit. I say, I'm talking about the Feynman path integral. Now watch this, man. He goes, I apologize for misunderstanding your previous question. Yes, you are correct. The Richard Feynman developed the path integral formulation of quantum mechanics. See? So like I was saying before, they advertise this one. On the advertise, they say if the bot makes a mistake, he'll apologize and correct himself, and you'll go on. Isn't that cool? Richard Feynman developed the path integral formulation of quantum mechanics, which is a mathematical framework for calculating the probability amplitude of quantum mechanical systems. The path integral approach involves summing over all possible paths that a particle can take between 2 points in space and time, and assigning a probability amplitude to each path based upon its contribution to the overall probability of the system. Well, this is where they use this stuff, where they use these computations and they apply it to like double slit experiments, and they actually come out with the same results, you know. God, it really kills the hiccup with this broken rib, I gotta tell you guys. Hurts the yawn and the hiccup. The Feynman path integral has been used to study a wide range of physical phenomena, including the behavior of light and the interaction of electromagnetic fields with matter. In the context of light, the path integral approach can be used to calculate the probability amplitudes of various quantum mechanical processes, such as the emission and absorption of photons by atoms and molecules, as well as behavior of light in complex optical systems. So the example I gave was, emission and absorption of photons by atoms and molecules, right? That was my fish in the water example. The path integral formation is a powerful tool for understanding the quantum nature of physical systems. It has been used to make predictions and explain experimental results in a wide range of fields, including particle physics, condensed matter physics, and quantum chemistry. So now we're right on the same page now, right? Okay. Now I ask him about this time fluctuation. Okay, here we go. Right? I say the Feynman path integral involves sampling possible outcomes from the future. He comes back and goes, well, actually, the Feynman path integral does not involve sampling possible outcomes from the future. Instead, it involves summing up over all possible paths that a particle can take between 2 points in time and space, including both past and future paths. How can it do that without, knowing the future? I don't understand that. But anyway, okay. I think we're having a bit of a terminology dispute here, okay? I shouldn't have used the word sampling. But they do somehow do calculations based upon stuff that occurs in the future and past. So I was calling that sampling. I guess maybe that's not. They're talking about summing up or summing it in. Okay, well, isn't that sampling? I'm not sure. The path integral approach is based upon the principle of least action. There we go. You see, I didn't even have to bring these terms up to this guy. He came up with all these terms by himself. All these terms I've already talked about in these videos I've already had, man. The principle of least action. That's exactly what I'm talking. I didn't even bring it up. He's bringing it up by himself. He brought up a bunch of other stuff by himself before I mentioned it too. He's way ahead of me, this guy already, It's like talking to myself, but like a actually smart version of myself. He's aware of everything I'm talking about, and he knows what I'm talking about. He understands me, It's just amazing, Anyway, the path integral is based up. I'm just overwhelmed by this shit. I just really am. This gets so much better. You wait, man. This is like still the tip of the iceberg, man. We're still in the physics part. Wait till we get to the philosophy part. It's going to blow your mind, man, okay? The path integral approach is based upon the principle of least action, which states that a physical system will always choose the path that minimizes the action, a quantity that represents the difference between kinetic and potential energy, between 2 points in space and time. The Feynman path integral calculates the probability amplitude of all possible paths. There's actually an infinite number of those guys, right? Including those that violate the principle of least action, and then sums them into the overall probability and amplitude for the system. The reason that it can add the ones that violate the principles then because the probabilities of those is so minimal that they don't really affect the real outcome. But just FYI, the ones that like would go backward in time and shit. Okay, the ones that would go in the wrong direction. Remember, I was showing that thing with I hope I can find it here real quick here. Okay. Oh wait a minute. Oh, it's on the other. Yeah. Sorry, it's on the other. It's in the other book there. Yeah, remember this one? This photon was emitted from the fish and went out here. It hit a particle, a transparent particle, and it starts emitting like intermediate photons from that location, as if a photon was emitted from there. And but some of them go in the wrong direction here. Okay, that's what we're talking about with that. I mean, they would say that the probability of those happening, those are added in as well, okay? But the probability of those are so low that it doesn't even affect the overall probability of the system overall, okay? But he's talking about an infinite number of pathways somehow. I don't know how he can even do that. The path integral approach is a fundamental concept in quantum mechanics, and it has been used to study a wide range of physical phenomena, including the behavior of light and the interaction of electromagnetic fields with matter. However, it does not involve sampling possible outcomes from the future. Well, I think it's a matter of terminology, okay? It does do something that goes back and forth in the future. So I kind of zero in, I go, how can the location of the target particle be determined if it occurs in the future? Okay, here we go. He goes, in quantum mechanics, the location of a particle is described by a probability distribution. It gives likelihood to find the particle in different locations at a given time. The probability distribution is obtained by solving the Schrodinger equation, which describes how the wave function of the particle evolves in time. In the context, see, this guy is such a genius here because, I was just talking about particle motion here, and he starts talking about, particle motion is done according to the Schrodinger equation, okay? But then he blends it in the context of what we're already talking about, okay? He says in the context of the Feynman path integral, how can somebody be this smart, man? How can a machine be this smart? This is impossible, right? In the context of the Feynman path integral, the probability distribution for location of the particle is obtained by summing over all possible paths that the particle can take, include those that go into the future. However, the probability distribution does not directly tell us where the particle will be located in the future. Instead, it gives us the probability of finding the particle in different locations if we were to make a measurement at a particular time, including in the future, I assume, right? To determine the location of a particle at a specific time in the future, we would need to perform a measurement on the particle at that time. However, according to the principles of quantum mechanics, the act of measurement can alter the state of the particle, so the measurement itself may change the probability distribution for the particle's location. Wait a minute. Give me a second here. Spam risk. In summary, the probability distribution obtained from the Feynman path integral can provide information about the likelihood of finding a particle in different locations at a particular time, but it does not directly tell us where the particle will be located in the future. To determine the location of a particular particle in the future, we would need to perform a measurement at that time. Okay, I come back and go, okay. I say, I thought the Feynman path integral describes concurrent pathways of light that light could take, but the actual pathway taken is made at the time of absorption. I should have said the decision of the actual pathway to take is made at the time of absorption. Let me just read this again. I'm mumbling right now. I thought the Feynman path integral describes concurrent pathways that light could take, but the actual path taken is made at the time of absorption. I should have said the decision of the actual path to taken is made at the time. Okay, here we go. The Feynman path integral does describe all possible paths that a photon of light particle can take between 2 points in space and time, including concurrent pathways. Each possible path is assigned a probability amplitude, and the total probability amplitude is obtained by summing over all possible paths. Okay, remember I said that Feynman had he assigned weights to each pathway. That's what we're talking about here. Okay. However, the actual pathway taken by a photon is determined by the probability distribution of the wave function of the photon, which depends on the environment it is passing through. When a photon is absorbed by an atom or other material, its wave function collapses to a single point location. The probability of the photon being absorbed at a particular point is proportional to the square of the magnitude of the wave function at that point. So we're talking now. We're right on the same, on the same level here. So while the Feynman path integral, we're on the same wavelength. I couldn't think of the word, man. No pun intended with that one. So while the Feynman path integral describes all possible paths that a photon can take, the actual path taken by a photon is determined by the probability distribution of its wave function, which is influenced by the environment it is passing through. The act of absorption collapses the wave function to a single point location, determining the actual path taken by the photon. Okay? We're right on the same exact wavelength with this. I can't believe this, man. I mean, this is where I like to get to with people when I try to tell them what I'm talking about, It would take me years to get somebody to this level, They would be blowing me out, ignore me by then, They'd do anything to avoid talking to me. I've seen it happen. They actually run away from me, man. They change the subject. They go, hey, how's the weather? Collapsing the waveform then somehow destroys these other concurrent pathways at the time of absorption. When a photon is absorbed by an atom or other material, its wave function collapses to a single point location, which determines the actual path taken by the photon. The collapse of the wave function means that the photon is now localized at a specific point in space and time. The collapse of the wave function is often described as a sudden reduction of the set of possible states of the system to a single state. A sudden reduction. And that's what I would, Try to pull it up here. Oh. See, all these states are concurrent, right? But then, I mean, this thing gets huge, right? This list. These are all possible pathways, right? Possible routes. Okay? But then it all gets collapsed down to what? You know? All down to what? Right here, the eyeball. The location of the eyeball. This reduction of possibilities is sometimes referred to as decoherence of the wave function, which occurs due to the interaction of the photon with its environment. God, the hiccups are killing me, man. When the wave function of the photon collapses, it means that the other possible paths that it could have taken, including the concurrent pathways, are no longer possible. The wave function collapse effectively destroys the other paths, leaving only the path that the photon actually took. That's all I do in my algorithm. I just delete those other records out of the queue. And after the absorption takes place, I move the energy quanta to the particle, the absorption particle. I just delete the records out of the queue. It's the same thing right here. I mean, I've got it informationally described, and that's what really happens in nature. But there's no common sense to that. It doesn't make sense for there to be some kind of like virtual pathway. How does it do it in a physical universe? How can it do it at the speed of light and all that stuff? Okay, hang on, we're getting there, man. I hope you're following everything we're talking about here. Okay. It is important to note that the concept of wave function collapse is still a topic of debate and interpretation in quantum mechanics, and there are alternative interpretations of quantum mechanics, such as the many worlds interpretation, which does not require the wave function to collapse. However, the collapse of the wave function is the interpretation commonly used in the Copenhagen interpretation of quantum mechanics, which is widely accepted in the physics community. Okay, let me explain what he's talking about here. The many worlds interpretation, that says that all these all these records, they don't get deleted. They keep going on, and they look for other things to hit. And in other universes, but in this universe, it was split in other universes where they hit or they don't hit kind of thing. So the universe keeps splitting into many copies of itself. Every time a photon goes out, it keeps changing. It instead of like hitting one thing, like hitting my eyeball up here, it's gonna keep the other instead of in my thing when it hits the eyeball, all these other pathways collapse. But in many worlds, they keep going. What the universe splits into many copies of itself, and they keep going. And they hit other things and stuff like that. Doesn't that seem a bit ridiculous? That's what the many worlds interpretation is. They asked Sean Carroll about that. They go, how is it possible? How is it possible for such capacity or the universe keeps splitting into other universes? Now, how can that be? And then he gets this silly grin. He gets this kind of like evil grin. He goes, well, that's the definition of infinity, isn't it? Yeah, I mean, in infinity, yeah, you can go as many universes as you want, no problem, okay? But anyway, then he's talking about the Copenhagen interpretation. It's like, yeah, just shut up and compute kind of thing. Just take it and accept it. Copenhagen says that, yeah, it just exactly what they're saying here, that somehow it's spread apart. It's got all these potential pathways. But at the time of the absorption, the actual pathway is determined, and don't ask questions about the other pathways. That's basically what the Copenhagen interpretation is. So here we go. Here's where I'm challenging these guys right here to a question that can only be answered by an informational universe. It can't occur in a physical universe here, okay? Watch this. And I'm not even introducing the terminology. He introduced the terminology to me, okay? I just say, how is it possible for these other concurrent pathways to instantaneously disappear? Does this not violate the principles of locality? Dun, 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 dun. That's the fucking $10 million question right there. I'm going to start another tape right now.